Hi everybody, this is Dr. K. This is my first video in my YouTube channel Mathematics with Dr. K. In this video we are going to show that a closed ball is a closed set. We start inside a metric space which is a set X, a non-empty set X, equipped with a metric function or distance called d, and we take any element x inside the metric space x and two positive real numbers here, epsilon and r. We know that the set of all the elements y in x that have distance from x strictly less than epsilon is a subset of x that is called an epsilon, the epsilon neighborhood of little x. And it is a well-known fact that this set is actually an open set in the metric space X. Now, a graphical illustration of such a neighborhood, I will usually write n-hood for neighborhood. A graphical illustration of such a neighborhood is what? We take X here, and we represent the neighborhood as a disk that has center X, radius epsilon, and of course the disk does not include the perimeter. It does not include the perimeter because we do have here strict inequality. Now, if we modify this definition slightly, and we actually include also points on the perimeter of a disk, then we take another set that it is called a closed ball. So the closed ball of a point X with radius R is what? It is the set of all the elements Y inside X that have distance from X less than or equal to R. The graphical or a graphical illustration of such a closed ball is actually a disk with center X, radius R, and now we include all the points in the perimeter are included. Now, what we are going to do in this video, we are going to show that the closed ball is actually a closed set in the metric space XD. Before, and this is really the statement we want to show, that given a metric space XD, a metric space, recall, is a pair. That means a set, a non-empty set, equipped with a distance function. So we are in a metric space. Take any point in the metric space. Here we take little x and the positive real number. This set is called the closed ball at X with radius R. It is the set of all the elements Y in X that have distance from X less than or equal to R. And we are going to show that this closed ball is actually a closed set in the metric space. What does it mean that the closed ball is a closed set? Well, by the definition of the closed set, this means that the complement of the closed ball is an open set in the metric space. Here we use the definition that a set F is closed if and only if the complement of the F is open, where F, of course, is a subset of our metric space X. So this is the definition of a closed set we are using here. There are other definitions of a closed set that are equivalent to this one, and it is possible to use these other definitions to show that the closed ball is a closed set. In this video, we are going to use this definition, which is probably the simplest one, because we only need to know what is an open set in order to show that the closed ball is a closed set. Before we move on with the actual proof, let's just highlight two things. We said by the definition of the closed ball that y is an element of the closed ball if and only if the distance between x and y is less than or equal to r. And similarly, we have that y is an element of the complement of the closed ball if, of course, y is not an element of the closed ball, which means that a point y is an element of the complement of the closed ball if and only if the distance between x and y is greater than r. So y is in the closed ball if this distance is less than or equal to r, and it is not in the closed ball if this distance is strictly greater than r. Okay, before we move on with the proof, just a piece of advice. Whenever you have a statement to show, or you have a proof to read, it's important to go on the statement you have and make sure you understand all the key terms in the statement. The key terms here are what? Metric space, distance functions, closed set, open set. And so it's important before also you continue with this video to make sure that you understand the meaning of all of these terms. The term of closed ball is the term that we just introduced, and so it's considered in the context of this video, it's considered to be a new term. Okay, so make sure you know exactly what each of and every of these terms mean. All right, so how we are going to show that the closed ball is a closed set? Well, as we said, we're going to show it by showing that its complement is an open set. And now here is a graphical illustration of what we have. We have our universal set, our metric space X. This whole thing here is X, this rectangle. Here we have our closed ball, and whatever is left in X, if we take away the closed ball, that means all of this area here, this is the complement of the closed ball. And we want to show that this set here is actually open. How we are going to show that the closed ball is open? Simply, we are going to apply the definition of the open set, which says that if we take any element inside the closed ball, so the closed ball is going to be open only if we are able, when we take any element in the closed ball, and for any element we can find a positive number, say epsilon, so that the epsilon neighborhood of these points W is all included in the closed ball. The closed ball, we said it is this set. The neighborhood of W, the epsilon neighborhood of W is this set. Okay, so really what we want to do, we want to find an epsilon, just one epsilon, not two, just one, an epsilon, so that the neighborhood of the epsilon neighborhood of W is all inside the complement of the closed ball. And here we can see from the graph, from our graphical illustration, that if we take any W inside the complement of the closed ball, it is actually possible to find a neighborhood, an epsilon neighborhood around W, that it is all included in the complement of the closed ball. But this is, although this is very helpful for our intuition, is not enough for a proof. And what we have to do next, what we are going to do next, is we will actually, by using the graphical illustration, we are actually going to identify an epsilon for which this is actually true, or this is true here. All right, so let's move on. And here we start. So what we said, we want to show now that the complement of the closed ball is an open set. Okay, so this is what we need to show. I just put here the definition of the open set as a reminder. And so we start with W. W is in the complement of the closed ball, which means, of course, that the distance between X and W is strictly greater than R. This is the distance between X and W is strictly greater than R. Now, we can see here that because the distance between X and W is strictly greater than R, if I take a neighborhood around W that has, let's say, radius from here to here, then this neighborhood is going to be all inside the complement of the closed ball. It's not going to intersect the closed ball. It's not going to go this way. It's not going to even touch the closed ball. Why? Because the neighborhoods actually do not include the perimeter of the disk. So the perimeter of the disk here is not included. Now, what is this epsilon equal to here in our graph? Well, this epsilon is what? You take the distance between X and W, take away R. From here to here, the distance is R. From here to here, the distance is R. So take away R, and what is left, call it epsilon. Well, this is exactly what we do here. W is in the complement of the closed ball. That means that the distance between X and W is greater than R. Now, from this inequality, subtract from both sides R, and what do we get? We get that the difference between this distance and R is a positive number, and I call this positive number epsilon. Now, from this equality, we also see that the distance between X and W is what? It is R plus our newly found epsilon. Now, from the graphical illustration, we see that this epsilon neighborhood of W, this is the epsilon neighborhood of W, is all inside the complement of the closed ball. So from the graphical illustration is clear. However, we actually need to show that. So this is our claim that this epsilon neighborhood for this epsilon is all inside the complement of the closed ball. And how do we show that one set is inside another set? That this set is a subset of this set over here. Well, whenever we have to do such, we have to show such a statement, what we do, we take any element of the set we think that it is smaller. That means we take, let's say, a z, that it is inside here, a z, that it is inside our neighborhood, and using some logical steps, we try to show that this z is also an element of the set we think that it is bigger. Before we move on, let's just recall that Z is inside this neighborhood is the same as saying that the distance between Z and W is less than epsilon. And then to say that Z is inside the complement of the closed ball is the same to say that the distance between Z and X is strictly greater than R. So that means we take a Z that has this property, and we would like to show that this same Z has this property. In other words, we really want to show this statement. This is what we want to show. If we take a Z that has distance from W less than epsilon, we want to show that this Z has distance from X greater than R. So this inclusion between these two sets ends up being is being expressed using them in as the two inequalities. This inequality implies this, and these are inequalities involving distances between 2 points. Okay, so Z in the neighborhood over here, the distance of Z from W is less than epsilon, and this is the distance between Z and W. It is, and we can see here it is less than epsilon, but this is also follows from the defining property of the neighborhood. Okay, now what do we have here? We actually have 3 points, X, W, and Z. And 3 points, of course, form a triangle. We know something about one of the sides of the triangle, the distance between X and W. We know something about the other side of the triangle, which represents the distance between Z and W. So this distance is equal to epsilon plus R. This distance, it is less than epsilon. And we want to find something about the distance between Z and X. This is the third side of the triangle, represents the distance between X and Z. Okay, is this greater than R? From our graphical illustration, it seems that it is, but we really have to show it analytically. Okay, so the triangle inequality satisfied by the distance function, the metric function d, says that this distance is less than or equal to this distance plus this distance. So this distance less than or equal to this one plus this one. Okay, and now we have an inequality involving 3 quantities. We know something about this quantity, we know something about this quantity, we want to figure out something about the third quantity. So what we are going to do, we are going to isolate this quantity on one hand, on the one side of our inequality, and we are leave the other two on the other side. And by doing that, we get that the distance between X and Z is greater or equal to the distance between XW minus the distance of Z between Z and W. So this guy is greater or equal to this distance minus this one. Okay, now I know that the distance between Z and W is less than epsilon. If I put a minus in front of this inequality, we are going to have that the distance minus the distance between Z and W is greater than minus epsilon. And so we take this from here, we go here, and then the next step, this distance is equal to that, epsilon plus R, substitute, and put the two together, epsilon plus R minus epsilon gives us R. So what we have shown that the distance between X and Z is strictly greater than R. Strictly greater than R. This distance strictly greater than R, which means that Z is not inside the closed ball with center X and radius R, is not inside here. And that means, of course, that Z is inside the complement of the closed ball. So this last step proves our claim that if epsilon is equal to this quantity, then this epsilon neighborhood of W is all inside is included to the complement of the closed ball with center X and radius R. Did we prove the claim? Okay, so I think it's clear that we prove the claim. Did we also show that the set, the complement of the closed ball is actually an open set? Yes, we did. And how did we do that? Well, let's just summarize what we have done so far. We took any element W, in the complement of the closed ball for that arbitrary element of the complement of the closed ball. We found a positive epsilon such that this epsilon neighborhood of W is all inside the complement of the closed ball. In other words, we have shown that for any W in the complement of the closed ball, there is an epsilon neighborhood of W that it is all contained in the complement of the closed ball. And this by definition says that the complement of the closed ball is an open set, and by implication and the definition of the closed set, it also shows that the closed ball is actually a closed set. That's the end of our proof. If you have any comments or any feedback, please leave them below. I will actually appreciate your comments and your feedback. Thanks for watching.